Welcome to This Explainer. If you've ever looked at a medical image and wondered, how in the world do invisible waves perfectly map the inside of a human body? Well, you are absolutely in the right place. Today, we're taking the foundational physics of matter and translating it into practical, clinically actionable knowledge. Let's kick things off with a crucial point from our source material. You simply cannot master the X-ray machine without first understanding the atom itself. Because, when you press that exposure button, you aren't just flipping on a light bulb. You are literally initiating a highly controlled microscopic collision. Now, I know exactly what you might be thinking right now. Oh no, physics again. It is a completely natural reaction to dread diving back into protons, neutrons, and wave equations. But stick with me here. I promise to show you exactly how these tiny, invisible interactions solve massive clinical challenges every single day in the radiology department. All right, here is our roadmap for today. We're going to cover the atomic blueprint, characteristic radiation explained, decoding the EM spectrum, beam quantity and quality, and finally, the inverse square law. Let's get right into it. Part 1, the atomic blueprint, the building blocks of imaging contrast. So we have to begin at the absolute smallest scale. We're talking about the atom, with its nucleus packed tightly with protons and neutrons and electrons orbiting in discrete shells. Now, understanding the Z number, or atomic number, is absolutely vital. The Z number is literally just the total number of protons in that nucleus. But why does this matter for an image? Well, because it completely dictates X-ray absorption. Take bone, for example. Bone contains calcium, which has a Z number of 20. Because 20 is relatively high compared to the elements making up your soft tissue, those calcium atoms absorb way more X-ray photons. That differential absorption is the exact reason why bone pops as crisp white on your final image, while the soft tissue fades into a dark gray. Now keep tungsten in mind. Tungsten has a massive Z number of 74 and a really tight K-shell binding energy of roughly 70 keV. This specific setup is exactly what allows diagnostic machines to function so efficiently. Binding energy basically just means how hard those innermost electrons are holding on to the nucleus. We measure all of this energy in kiloelectron volts, or keV, with our standard diagnostic machines operating in a sweet spot between 20 and 150 keV. Moving on to part 2, characteristic radiation explained. We call this the cascade reaction. I want you to visualize the exact moment an incoming electron from your machine's cathode actually slams into our tungsten target. First, that incoming high-energy electron comes in with enough force to completely knock an inner K-shell electron right out of its orbit. Boom! This sudden vacancy leaves the atom super unstable, and atoms hate being unstable. So, an electron from an outer shell, like L or M, rapidly drops down to fill that hole. And here is where the magic happens. The exact energy difference between those two shells has to go somewhere, right? It's released as a fixed energy X-ray photon. We call this step-by-step process characteristic radiation because the resulting photon's energy is entirely dictated by the unique atomic structure of the target element. The really cool part is that we can actually manipulate this physics to our advantage. If we use tungsten, we get characteristic peaks at 59 and 68 keV, which is perfect for standard diagnostics. But look what happens if we simply swap the target material out for molybdenum. The characteristic peaks shift drastically down to between 17 and 19 keV. These much lower energy peaks are absolutely perfect for highlighting delicate differences in soft tissue. And that's exactly why molybdenum is the absolute go-to material for mammography. But here's a staggering reality check from inside the X-ray tube itself. Over 99% of the incoming electron kinetic energy hitting that anode doesn't even become radiation at all. It is converted purely into heat. 99%. That leaves less than 1% of that massive energy wave to actually become the useful X-ray radiation we need to create our image. It's crazy. This incredible inefficiency is exactly why thermal energy management, like complex anode cooling systems and specialized tube designs, is absolutely critical. Without it, the machine would literally melt itself down. All right, part 3, decoding the EM spectrum. Let's see where X-rays actually live. So all electromagnetic waves, whether we're talking about radio waves, visible light, or X-rays, share a few key traits. They all travel at the speed of light in a vacuum, which is a blistering 3 times 10 to the 8th power meters per second. And they all consist of oscillating perpendicular electric and magnetic fields. But what really separates them? It's their frequency and their wavelength. Planck's equation, E equals hf, tells us that energy is directly proportional to frequency. Because X-rays sit way up at the extreme high-frequency end of the spectrum with incredibly tiny wavelengths between 0.01 and 10 nanometers, they carry immense energy per photon, literally enough energy to strip electrons completely away from atoms, which is exactly what makes them ionizing. This actually brings us to a really fascinating comparison. X-rays versus gamma rays. They actually overlap in energy and wavelength at the top of the spectrum. So what's the actual difference? It is entirely about their origin story. X-rays originate outside the nucleus. They're produced by those electron interactions we were just talking about. Gamma rays, on the other hand, originate from inside the nucleus, born from radioactive nuclear decay. While both waves are heavily ionizing and require some serious shielding, their totally different origins perfectly explain why a nuclear medicine scanner looks and operates so differently from your plain diagnostic X-ray machine. Moving to part 4, beam quantity and quality. Time to master the control panel. When you finally step up to that control panel, you're primarily managing 2 things, quantity and quality. MAS, or milliampere seconds, controls beam quantity. That's the total number of X-ray photons you're producing. You double the MAS, you double the photon output. It's that simple. This directly dictates your image density, basically the overall darkness of the film. On the flip side, we have kVp, or kilovolts peak. This controls beam quality, the energy distribution of those photons. Higher kVp means higher energy photons. Now, raising kVp actually does increase both the quality and the quantity of photons to a degree, but remember this, its dominant clinical effect is always on the beam's penetrating power, which dictates your subject contrast. And this highlights a classic clinical trade-off we face every single day. Higher kVp gives great penetration and actually results in a lower patient dose for a given density. That's why for a chest X-ray, where the lungs are mostly full of air and provide naturally high contrast anyway, we crank the kVp way up to between 110 and 125. But if you tried that on a hand or an ankle, that high energy would completely blow right through the delicate structures. You have to purposefully drop the kVp down between 50 and 65 for extremities just to preserve that subtle, vital contrast between the bone and the soft tissue. Finally, part 5, the inverse square law. Let's look at the macro environment. The inverse square law is a completely non-negotiable rule of physics. It states that beam intensity falls off with the square of the distance from the X-ray source. Put simply, if you double your distance from the source, the radiation intensity doesn't just cut in half, it drops drastically to 1/4 of its original strength. And this law isn't just fun trivia. It grounds all of that heavy physics directly into your daily clinical habits. Think about radiation protection. Taking just one large step back when the machine fires exponentially reduces your personal exposure dose. Or think about image geometry. Altering your source-to-image distance, or SID, directly impacts both the density of your image and the geometric sharpness of the anatomy you're capturing. So, I want to leave you with a final thought to reflect on regarding your own daily practice. Based on the immense, undeniable power of the inverse square law, are you truly maximizing your distance to ensure your own clinical safety every single time that machine fires? I hope this explainer has shown you how mastering the tiny, invisible atom really does give you ultimate practical control over the entire imaging process. Thanks for tuning in.